Hi everyone, this is my first video and I'm starting on topic 6, equilibria, which follows on from the topic we were doing just before we broke up, kinetics. So I'm going to be using your textbook, which is available online, and also your CGP revision guide that was given just before we broke up, and I'm going to be doing some of the examples from that revision guide to help you understand the topic. Equilibria is the study of how far a reaction will go, and it's important in chemical industry because using equilibria, the principles of equilibria, Le Chatelier's principle, which is you're familiar with from GCSE, and the equilibrium constant calculations, we can calculate how to get the maximum yield of product for the lowest cost and the quickest time, which of course is really important to any kind of industrial chemist. So some things that I'm going to assume you remember from GCSE, well I say assume, I'm going to recap them very briefly, is that you understand what a reversible reaction is, for one. So what we mean by that is that instead of taking A and B, reacting them together and the reaction happening, you get C and D and it's finishing, many reactions actually occur in equilibrium, or they're reversible, sorry. So that means that you have A and B, react them together and get C and D. And to start with, that reaction is quite quick because you've got lots of A and B, thinking about collision theory, lots of successful collisions. And so you make lots of C and D. And then when you started to make C and D, collisions happen on that side of the reaction and they react backwards to get A and B as well. So that is the case for many reactions. And we show that a reaction is reversible by using these forward and backwards arrows here. Now I've just got a generic reaction on the board just to kind of give you a few examples, just to go through the examples, but I will show you which reactions you'll need to know for your A level as we go through the topic. So some key points that I've written down the side here is that what's called a dynamic equilibrium. So what do we mean by that? What we mean is that this reaction has happened, A and B have reacted together and we've made the products, C and D. C and D have reacted together and they've gone, made the reactants again, A and B. And that has happened over the course of a time. You leave the reaction to occur, to run its course, and eventually you reach this dynamic equilibrium. And what that means is that the concentrations of the reactants and the concentrations of the products are constant. That doesn't mean they're equal to each other. You could have a really high concentration of reactants and a really low concentration of products. So long as those concentrations don't change anymore, you're then in a position of dynamic equilibrium. The other point to note and to make sure you remember is the rate of the forward reaction and the rate of the backwards reaction are equal to each other. And if you think about it, they would have to be equal to each other for those concentrations to remain constant. So the two things, the concentration of the reactants and products are constant, and the second, the rate of the forward reaction and the rate of the backwards reaction are equal to each other. Okay? The third bit of information to remember that you need to know is that in order for a reaction to reach dynamic equilibrium, it has to be a closed system. And what we mean by a closed system is that none of the reactants or the products can escape. So if it's a reaction involving gases, then you would have to have a lid or a gas syringe, using a gas syringe so the gas can't escape. And if it's a reaction involving solutions, that none is able to leak out anywhere, so your containers are suitable. So three things: closed system, the concentration of the reactants and the concentration of the products are constant, and the rate of the forward reaction equals the rate of the backwards reaction. I'm going to turn the video off there and then I'm going to come back and talk about Le Chatelier's principle and how changing conditions affects the position of that equilibrium.